Very few people know that Vikings possessed a building design so sophisticated that their longhouses stayed warm during winters when temperatures plunged to deadly lows, and remarkably cool during summers when the same structures should have turned into unbearable ovens. Even fewer realize this wasn't accidental or lucky. It was intentional architectural engineering that solved a problem modern buildings with all their technology and expensive materials still struggle with: maintaining comfortable temperatures year-round without consuming massive amounts of energy. Before we reveal the specific design secret that made this possible, drop a comment with where you're watching from. And if stories of lost ancient technology fascinate you, hit that subscribe button, because what you're about to learn will change how you think about building design, thermal comfort, and what primitive people actually understood about physics. The secret wasn't just thick walls, though Vikings had those. It wasn't simply a good fireplace, though their heating systems were remarkably effective. It was something far more ingenious: a specific architectural feature that worked with natural heat flows, seasonal changes, and the physics of thermal mass in ways that wouldn't be formally understood by science for another 1,000 years. A design element so effective that when modern researchers reconstructed Viking longhouses using period-accurate methods and actually lived in them through full seasonal cycles, they were shocked by how well the climate control worked. Here's what makes this story truly remarkable: this knowledge almost disappeared completely. For centuries, historians assumed Viking longhouses were simply crude shelters, dark, smoky, uncomfortable structures where people merely survived rather than thrived. But archaeological evidence combined with experimental reconstruction has revealed something completely different. Vikings had figured out principles of passive climate control, thermal mass management, and seasonal adaptation that most modern architects don't understand even today. And the buildings they created using these principles? They maintained relatively stable interior temperatures despite exterior temperature swings of 50 to 60 degrees Celsius between summer and winter. They did this using no technology beyond careful observation, natural materials, and sophisticated understanding of how heat actually moves through structures. To understand why this design secret mattered so profoundly, you first need to understand the brutal problem Vikings faced. And it wasn't the problem most people think. Everyone knows Scandinavian winters were harsh. Temperatures routinely dropped to -20 degrees Celsius or lower. Snow accumulated for months. Darkness dominated during the polar winter when the sun barely rose. These conditions required buildings that could retain warmth, and Vikings certainly addressed that challenge. But here's what very few people realize: Scandinavian summers, particularly in the southern regions where many Vikings lived, could be surprisingly warm. Temperatures regularly reached 25 to 30 degrees Celsius, sometimes higher. And when you're living inside a structure with thick walls designed to trap heat, those summer temperatures created a serious problem. The same building that needed to hold precious warmth during 9-month winters could become an unbearable oven during the brief but intense summer months. The thick materials that prevented winter cold from penetrating also prevented summer heat from escaping. People who'd survived freezing temperatures would find themselves unable to sleep at night because their own shelter was too hot. This dual-season challenge, extreme cold in winter, uncomfortable heat in summer, required a solution that could work both ways. The building needed to trap heat when cold, release heat when warm, and transition between these modes as seasons changed. Most medieval construction failed completely at this task. Structures were optimized for one season or the other, but rarely both. Standard medieval building techniques across Europe focused almost exclusively on winter heating. Thick stone walls, small windows, large fireplaces, all designed to combat cold. These buildings worked reasonably well in winter but became stifling in summer. The thermal mass that stored winter warmth also stored summer heat, creating indoor temperatures that could exceed outdoor temperatures and last through the night. Vikings faced this same challenge, but with even more extreme temperature swings due to their northern latitude. A longhouse in Norway or Iceland might experience interior/exterior temperature differences of -30 degrees Celsius in winter and +30 degrees Celsius in summer. The same structure had to handle both extremes effectively, or it would be uninhabitable for significant portions of the year. So how did they solve it? The answer reveals a level of architectural sophistication that challenges everything we've been taught about primitive Norse builders. The secret began with something that seems counterintuitive. Vikings built many of their longhouses partially underground. Not completely subterranean like a dugout, but with the floor level excavated 50 to 100 centimeters below the surrounding ground surface. This single design decision solved multiple problems simultaneously and formed the foundation of their entire climate control system. By sinking the structure into the earth, Vikings accessed one of nature's most reliable climate moderators: ground temperature. Below the frost line, typically 60 to 100 centimeters in Scandinavia, ground temperature remains relatively constant year-round, usually around 8 to 12 degrees Celsius regardless of surface conditions. This stable temperature zone acts as a massive thermal battery that neither freezes in winter nor overheats in summer. When Vikings built with the floor partially below ground level, the earth itself became part of the building's thermal envelope. In winter, the ground at 10 degrees Celsius was dramatically warmer than air at minus 25 degrees Celsius. Heat loss from the living space into surrounding earth was far less than heat loss into frigid air. The earth acted as insulation, a buffer between the interior warmth and the killing cold outside. In summer, the principle reversed. When outside air reached 28 degrees Celsius, the ground at 10 degrees Celsius became a cooling sink. Heat naturally flowed from the warmer living space into the cooler earth, helping to moderate interior temperatures. The same earth that prevented winter heat loss now prevented summer heat buildup. But this was only the first layer of the Viking climate control system. The walls themselves revealed even more sophisticated understanding of thermal dynamics. Now, if you're already fascinated by this hidden Viking technology, make sure you're subscribed because we're about to reveal the complete architectural system that made year-round comfort possible using nothing but natural materials and brilliant design. Viking walls in the coldest regions weren't simple structures. They were complex, multi-layered assemblies that would impress modern building scientists. The standard construction that archaeologists have documented at sites across Scandinavia reveals a remarkably consistent pattern, one that demonstrates intentional design rather than random building. The outer wall was typically constructed from vertical wooden posts or horizontal logs forming the primary structural frame. But Vikings didn't stop there. They added layers upon layers of insulating materials, each serving a specific thermal purpose. The most critical element was turf, thick blocks of earth held together by dense grass root systems, cut from marshy areas where root density was highest. These turf blocks weren't just piled randomly. They were carefully stacked in layers, sometimes reaching thicknesses of 1 to 1.5 meters on the north and west walls that faced prevailing winter winds. Here's why this mattered. Turf is a remarkably effective insulator, but not for the reasons most people assume. It's not the earth itself that insulates. Soil conducts heat fairly readily. The insulation comes from the air trapped within the root matrix and between the layered blocks. Air is one of nature's best insulators, and the complex structure of root-bound turf creates thousands of tiny air pockets that prevent heat transfer. Archaeological excavations show that Vikings built these turf walls with specific layering patterns. A typical cross-section revealed by excavations at sites like Borg in Lofoten, Norway, shows an outer layer of turf blocks arranged vertically, then a middle layer of looser organic material, dried moss, heather, or even seaweed in coastal areas, creating additional air gaps, then an inner layer of turf blocks or sometimes wooden planking, creating what modern engineers would call a double wall with cavity insulation. This construction created multiple thermal barriers. Heat trying to escape the interior had to pass through the inner wall layer, then through the air-filled cavity with its organic insulation, then through the outer turf layer. Each transition slowed heat transfer. In winter, this meant interior warmth stayed inside. In summer, it meant exterior heat stayed outside. But the brilliance went further. Turf walls had another property that Vikings exploited: thermal mass combined with insulation. The earth in the turf blocks could store heat, but the air pockets prevented that heat from conducting through rapidly. This created a thermal lag, a delay between exterior temperature changes and interior temperature response. When a cold snap hit in winter, dropping exterior temperatures suddenly, the thermal mass in the walls prevented interior temperatures from dropping immediately. The building's temperature changed slowly, giving inhabitants time to adjust heating. Similarly, on a hot summer day, the walls absorbed heat slowly and released it even more slowly, preventing interior temperature spikes. Perhaps most remarkably, Vikings enhanced this effect in winter by allowing snow accumulation on the walls and roof. Snow is an excellent insulator. Its structure of ice crystals with air spaces creates insulation values similar to modern foam. A longhouse covered in 30 to 50 centimeters of snow became essentially a snow cave, with the snow layer adding another thermal barrier. Vikings didn't try to remove this snow. They understood it was helping them. The roof construction followed similar principles but solved additional challenges. A typical Viking roof excavated by archaeologists shows multiple distinct layers, each serving specific functions. The structural layer was wooden rafters and crossbeams creating the frame. On top of this came birch bark, not for insulation, but for waterproofing. Birch bark is naturally water-resistant and flexible, creating a moisture barrier that prevented rain and snowmelt from penetrating into the living space. Above the birch bark came the turf layers, typically 30 to 70 centimeters thick of the same root-bound earth used in walls. This created massive insulation overhead while adding significant thermal mass. A thick turf roof could weigh several tons, but it dramatically reduced heat loss through the roof, the direction where heat naturally wants to escape since warm air rises. In summer, this same roof prevented solar heat gain. The sun beating down on a turf roof heated the outer surface, but that heat had to penetrate through enormous thermal mass and insulation before reaching the interior. Most of the solar energy was absorbed by the turf, stored temporarily, and then radiated away at night when exterior temperatures dropped. This created a natural cooling cycle. During summer nights when outside air cooled to 12 to 15 degrees Celsius, the roof released its stored heat upward into the cool air. By morning, the roof had cooled significantly and could absorb another day's solar heat without transmitting it to the interior. The building essentially breathed with the daily temperature cycle. But the most ingenious element of Viking climate control, the true secret that very few people know about, involved the positioning and design of the heating system itself. And this is where Viking architectural understanding becomes genuinely impressive. Standard medieval construction placed fireplaces against outer walls, usually at the end of a building. This made construction easier and simplified chimney building. But it was thermally wasteful. A fireplace against an exterior wall radiates roughly half its heat directly into that wall, which then conducts much of that warmth straight outside. You're essentially heating the exterior environment as much as your interior space. Vikings designed their heating system completely differently, using a configuration called the langhold, the long hearth. Instead of a fireplace at one end, they created a long, shallow trench running down the center of the longhouse, lined with stones. This hearth could extend 10, 15, even 20 meters through the length of the building. This central positioning was brilliant for multiple reasons. First, all the heat radiated from the langhold stayed inside the building. There was no exterior wall to conduct warmth away. The fire's energy distributed evenly throughout the interior space, with no cold zones at the far end of the structure. Second, the stone lining of the hearth created significant thermal mass right in the center of the living space. Throughout the day, as the fire burned, these stones absorbed tremendous amounts of heat. They would remain hot for 8 to 12 hours after the fire died down, continuing to radiate warmth long after flames had gone out. This thermal battery effect meant Vikings didn't need to maintain constant fires. They could build hot fires for a few hours, heating the stone mass, then let the fires die down or go out completely while the stored heat maintained comfortable temperatures through the night. This dramatically reduced firewood consumption, a critical advantage when gathering fuel required dangerous work in harsh conditions. But here's where the seasonal adaptation becomes truly sophisticated. The same langhold that provided essential winter heating could be managed to avoid overheating in summer. During warm months, Vikings built minimal fires, only enough for cooking and only for brief periods. The central position of the hearth meant heat rose straight up toward the roof rather than collecting against walls. And this is where the final piece of the Viking climate control secret comes into play: strategic ventilation. Archaeological evidence shows that Viking longhouses had carefully positioned openings beyond the main door. Small gaps near the roofline on opposite walls allowed for cross-ventilation. In winter, these were sealed tight with wooden plugs and packed with insulating materials to prevent heat loss. In summer, they were opened. When opened, these high vents created natural airflow. Hot air rises, so the warmest air in the summer longhouse collected near the roof. By opening vents at the high points, this hot air could escape naturally. Cooler air entered through the doorway at floor level, creating circulation that prevented heat buildup. This wasn't random ventilation. The positioning was calculated. Vents on opposite walls created crossflow, ensuring air actually moved through the space rather than just leaking out one side. The height placement meant warm air escaped while cooler air near floor level remained relatively undisturbed. The combination of all these elements, partial underground construction, multi-layer insulated walls, thermal mass in turf and stone, central hearth positioning, and seasonal ventilation management, created a complete climate control system that maintained comfortable temperatures year-round. The synergy: when every element works together. Understanding individual components of Viking longhouse design is one thing. Understanding how they all work together as a complete, integrated system reveals the true genius of Norse architecture. Because the secret wasn't any single feature, it was how multiple design elements reinforced each other to create climate control that was genuinely sophisticated. Start with the thermal envelope, the complete barrier between interior and exterior. In a Viking longhouse, this envelope consisted of the earth surrounding the partially buried floor, providing stable base temperature, the multi-layer turf walls with their air-trapping insulation, the massive turf roof with its waterproofing and thermal mass, and the strategically positioned openings that could be sealed or opened as needed. This envelope didn't just block heat transfer. It modulated it, slowing the rate at which interior temperatures responded to exterior changes. This created what modern building scientists call thermal lag, the delay between outside temperature changes and inside temperature response. In practical terms, when exterior temperature dropped suddenly during a winter storm, interior temperature didn't crash immediately. The thermal mass in walls and roof absorbed some of the temperature difference, releasing stored heat inward while slowly cooling. This gave inhabitants time to increase fire, add insulation layers, or take other adaptive measures. The building didn't fail catastrophically when conditions worsened. The same principle worked in summer. On a hot afternoon when exterior temperatures spiked, the thermal mass absorbed heat slowly. Interior temperatures rose gradually, if at all, rather than spiking immediately. By the time the thermal mass had absorbed significant heat, evening arrived and exterior temperatures dropped, allowing the stored heat to radiate outward rather than inward. This thermal lag effect was enhanced by the specific positioning of different thermal masses. The langled stones in the center of the building had the shortest thermal lag. They heated quickly when fire burned and cooled relatively quickly after. This made them responsive, good for quick heat when needed. The turf walls had medium thermal lag. They took hours to absorb heat significantly and hours more to release it. This created stability, preventing rapid temperature swings. The earth surrounding the buried portion of the floor had the longest thermal lag of all. Ground temperature changed very slowly, providing a stable baseline that barely shifted even over weeks of extreme weather. These different response times working together created a layered thermal buffer. Quick response from hearthstones, medium-term stability from walls, and long-term baseline from earth. The combination meant interior temperatures could remain relatively stable even when exterior temperatures swung wildly. The airflow management completed the system. In winter, the longhouse was sealed tight. Every gap plugged, every vent closed. The building became an enclosed thermal envelope where heat could accumulate and persist. The only intentional opening was the smoke hole directly above the langled, sized just large enough to vent smoke while minimizing heat loss. Vikings managed this smoke hole carefully. When fire burned hot, they opened it wider to allow smoke to escape freely. When fire died down to coals or went out completely, they could partially close it with a wooden cover or stone slab, reducing heat loss while maintaining enough ventilation to prevent dangerous gas buildup. In summer, the strategy reversed completely. The high vents opened to release accumulated heat. The door could be left open during cooler morning and evening hours to flush out warm air and bring in cool. The smoke hole remained open constantly, creating a natural chimney effect that drew air upward and out. This seasonal adaptation meant the same structure could optimize for completely opposite conditions. Winter mode, sealed, heat-retaining, using thermal mass to store warmth. Summer mode, ventilated, heat-releasing, using thermal mass to buffer heat absorption. The archaeological evidence, proof it actually worked. For decades, historians assumed this level of sophistication was beyond Viking capabilities. Surely Norse builders just stacked logs or turf randomly, created crude shelters, and suffered through harsh conditions with minimal comfort. The idea that they developed intentional climate control systems seemed far-fetched. Then archaeologists started actually excavating Viking-age longhouses carefully, documenting construction techniques rather than just recovering artifacts. What they found was consistent, intentional design repeated across hundreds of sites spanning centuries and thousands of miles. At Borg in Lofoten, Norway, excavations revealed a chieftain's longhouse with walls showing clear multi-layer construction. The outer turf layer, inner wall layer, and insulating cavity between them were distinct in the soil stratigraphy. Measurements showed the north wall, facing prevailing winter winds, was significantly thicker than the south wall, intentional optimization for thermal protection. At Stong in Iceland, a longhouse buried by volcanic ash in 1104 AD was preserved in remarkable detail. The turf wall cross-sections showed not random earth piling, but carefully constructed layers with different materials serving different functions. The presence of heather and moss in the wall cavities, materials that had to be gathered deliberately and brought to the site, proved this wasn't accidental construction. The langled positioning in excavated longhouses showed remarkable consistency. In structures across Scandinavia, from Norway to Iceland to Greenland, the long hearth appeared in the central axis, never against exterior walls. The repetition across such geographic spread and time span indicates this was understood technique, not random variation. Perhaps most convincingly, modern experimental archaeology has validated the system's effectiveness. In the 1990s and 2000s, several groups reconstructed Viking longhouses using only period-accurate materials and techniques, then actually lived in them through full seasonal cycles to test their functionality. The Lofoten Viking Museum in Norway built a full-scale reconstruction of the Borg Chieftain's Hall. When researchers inhabited this structure through a Norwegian winter, interior temperatures remained 15 to 20 degrees Celsius warmer than exterior temperatures even with minimal fire use. The thick turf walls, central hearth, and partial earth sheltering created measurable thermal benefit. During summer months, the same structure stayed noticeably cooler than exterior temperatures during hot afternoons. Researchers documented interior temperatures 5 to 8 degrees Celsius below exterior peaks, despite the building having no active cooling. The thermal mass and ventilation strategy worked exactly as the design intended. Similar results came from reconstructions in Iceland and Denmark. The consistency of results across different latitudes and climates proved the design principles were sound, not just lucky accidents that worked in one specific location. Chemical analysis of soot deposits on excavated longhouse timbers revealed another detail that confirmed sophisticated use. The soot patterns showed that fires in the Langold burned intensely for relatively short periods rather than constantly. This matched the thermal mass strategy, hot fires to heat stones, then letting fires die while stones radiated stored warmth. Why the knowledge was nearly lost. Given how effective this design was, why did it nearly disappear from history? Why don't modern buildings incorporate these principles? The answer reveals how architectural knowledge can be lost even when it works brilliantly first. The Viking Age ended. As Scandinavian societies Christianized and centralized in the 11th to 13th centuries, building styles changed to match continental European norms. Stone churches and timber-framed buildings replaced traditional longhouses. The new styles reflected cultural shifts and new construction priorities, not necessarily thermal performance. Second, the knowledge was oral and practical, not written. Vikings didn't produce architectural treatises or construction manuals. Builders learned techniques by working with experienced craftsmen, observing, and practicing. When the tradition of building longhouses ended, that knowledge transmission chain broke. Within a few generations, nobody remembered why walls were built with multiple layers or why hearths were positioned centrally. Third, later historians misinterpreted the archaeological evidence. When 19th and early 20th century scholars found Viking longhouse remains, they saw crude earthen structures and assumed Vikings lived in primitive, uncomfortable conditions. The sophisticated thermal engineering wasn't obvious from degraded ruins. It took careful excavation, experimental reconstruction, and modern building science knowledge to recognize what Vikings had achieved. Fourth, industrial age construction brought new materials and methods that seemed superior. Why build thick turf walls when you could buy bricks? Why position hearths centrally when you could install iron stoves against walls? The old techniques seemed obsolete, so they were abandoned without anyone analyzing why they'd worked so well. Finally, climate control became an active rather than passive problem. As heating technology improved, first better stoves, then central heating, eventually electric and gas systems, buildings could maintain comfort through brute force energy consumption. Design sophistication mattered less when you could just burn more fuel or use more electricity. Modern relevance. Why this still matters. The Viking climate control system isn't just historical curiosity. The principles they understood and applied remain valid and increasingly relevant as modern construction faces energy efficiency and sustainability challenges. Consider the earth sheltering technique. Modern earth-sheltered or bermed homes use the same principle Vikings employed, partially burying structures to access stable ground temperature. Contemporary sustainable architecture has rediscovered this as an energy-saving strategy, though Vikings figured it out a millennium earlier. The multi-layer wall construction with air cavities directly parallels modern insulated wall systems. Contemporary building codes require wall assemblies with separate layers for structure, insulation, and weather protection. Vikings built exactly this type of assembly using available natural materials. Thermal mass for climate control is experiencing renewed interest in green building design. The concept of heating mass during energy-abundant periods, sunny afternoons, off-peak electricity hours, and releasing that stored energy when needed matches exactly what Vikings did with their stone langled. Natural ventilation strategies are being incorporated into modern passive house design and sustainable architecture. The principle of using stack effect, hot air rising, to create airflow without mechanical systems is thousands of years old, but contemporary architects are relearning its value. The key insight Vikings understood, that buildings should work with natural heat flows and seasonal cycles rather than fighting them with constant energy input, represents a fundamental principle that modern construction is slowly rediscovering. A Viking longhouse required perhaps 1/10 the firewood consumption of a poorly designed cabin for equivalent comfort. Translated to modern terms, that's a 90% reduction in heating energy use. Contemporary building science aims for exactly this type of dramatic efficiency improvement through passive design. Practical applications today. Can these Viking principles be applied to modern construction? Absolutely. Here are specific techniques that work today. Partial earth sheltering. Building into hillsides or berming earth against north-facing walls provides free insulation and access to stable ground temperature. This works in any climate where ground temperature differs significantly from air temperature extremes. Thermal mass positioning. Placing high thermal mass materials, stone, concrete, brick, inside the insulated envelope rather than outside allows those materials to store and release heat beneficially. A stone floor or wall inside an insulated house acts like Vikings' langled stones, storing warmth for later release. Multi-layer wall systems. Creating wall assemblies with multiple barriers and air cavities provides better insulation than single-layer construction. Modern insulation products make this easier, but the principle remains: trap air, create barriers, slow heat transfer. Central heating mass. Modern versions include masonry heaters, thermal storage tanks for solar systems, or heated concrete slabs. All use the Viking principle of heating mass during energy-abundant times and releasing stored energy later. Natural ventilation design. Positioning openings to create stack-effect airflow reduces cooling energy needs. High vents for hot air exhaust, low openings for cool air intake, the same strategy Vikings used 1,000 years ago. Seasonal operation modes. Designing buildings that can transition between sealed winter mode and ventilated summer mode improves year-round comfort with less energy. Operable windows, closable vents, and adjustable shading allow this flexibility. Living roofs. Green roofs. The modern version of Viking turf roofs provides insulation, thermal mass, stormwater management, and aesthetic benefits. The principle is identical. Use earth and vegetation as a multifunctional roof covering. The legacy and spread of knowledge. Viking architectural knowledge didn't die completely. It persisted in remote areas where traditional building methods continued long after the Viking Age ended. In Iceland, turf construction remained standard for most buildings well into the 20th century. Icelandic turf houses built in the 1800s and early 1900s used fundamentally the same techniques as Viking longhouses: thick turf walls, multi-layer construction, central hearth positioning. The knowledge survived through practical necessity in a place where timber was scarce and climate was harsh. Some of these Icelandic turf houses are still standing and some even still inhabited. They prove the durability of the construction method and its continued functionality. Modern analysis of these structures has helped historians understand how Viking buildings worked, since the Icelandic examples preserved techniques that had disappeared elsewhere. In Norway, traditional construction called lofthus, log buildings, incorporated elements of Viking design even as overall building styles evolved. The practice of using moss or turf for insulation between logs, the preference for thick walls, and careful attention to positioning and orientation all echoed older traditions. The knowledge also influenced construction in areas where Vikings settled. In the Norse settlements of Greenland, Iceland, and even briefly in North America, colonists built using longhouse principles adapted to local conditions. Archaeological sites show these settlers applying familiar techniques with available materials. When Norse influence faded, some knowledge transferred to local populations. Indigenous peoples in areas of contact sometimes adopted elements of Viking construction that proved useful. The sharing went both directions. Vikings had learned from indigenous builders too, creating cross-cultural knowledge exchange. The larger lesson: indigenous knowledge and primitive technology. The Viking longhouse climate control story illustrates a broader point about historical technology that deserves emphasis. So-called primitive or traditional builders often understood principles that modern society has forgotten or struggles to replicate. Vikings had no thermodynamics textbooks, no building science degrees, no computer modeling software. But through careful observation, experimentation, and intergenerational knowledge transmission, they developed building techniques that solved complex thermal challenges extremely effectively. This pattern repeats across cultures. Indigenous Arctic peoples developed sophisticated cold-weather architecture. Desert cultures created buildings that stayed cool in extreme heat. Tropical builders designed structures that managed humidity and ventilation. Each tradition represented accumulated wisdom refined over centuries of practical experience. Modern architecture, despite tremendous advances in materials and analytical tools, sometimes loses sight of these fundamental principles. We can build buildings that require enormous energy inputs to maintain comfort rather than buildings designed to work with climate naturally. The rediscovery of Viking climate control techniques, and similar wisdom from other traditional building cultures, isn't about romantically returning to the past. It's about learning from proven solutions to problems we still face. Energy efficiency, sustainability, resilience, comfort. Vikings achieved all these with natural materials and careful design. Conclusion: the secret revealed. So what was the Viking secret design that made longhouses work in both summer and winter? It wasn't any single element. It was the integration of multiple principles. Using earth sheltering to access stable ground temperature. Building multi-layer walls with trapped air for insulation. Incorporating massive thermal mass inside the insulated envelope. Positioning the heating system centrally rather than against exterior walls. Creating roof systems that insulated while managing moisture. Designing for seasonal ventilation that could be opened or sealed as needed. Every element reinforced the others. The partial underground construction made the thick walls more effective. The thick walls made the central hearth more efficient. The central hearth made the thermal mass more useful. The thermal mass made the ventilation strategy more successful. This integration created buildings that maintained comfortable interior conditions year-round with minimal energy input. Vikings achieved what modern green building strives for: passive climate control through intelligent design rather than brute force mechanical systems. The knowledge nearly disappeared because it was practical rather than theoretical, oral rather than written, traditional rather than innovative by later standards. But archaeological evidence and experimental reconstruction have revealed the sophistication of what Vikings accomplished. Their longhouses weren't crude shelters where people barely survived. They were carefully engineered structures that created genuine comfort in one of Earth's most challenging climates, using nothing but available natural materials and deep understanding of how heat, air, and mass interact. That's the real secret. Not any magic material or lost technology, but simply understanding natural principles deeply enough to work with them rather than against them. Vikings observed how heat moved, how materials behaved, how seasons changed. They designed buildings that aligned with those realities instead of fighting them. Modern construction is slowly relearning these lessons. Earth-sheltered homes, thermal mass heating, natural ventilation, multi-layer insulation, seasonal operation modes, all these contemporary innovations were standard practice in Viking architecture 1,000 years ago. The longhouses are gone, reduced to grass-covered mounds or excavated ruins. But the knowledge they represented, the understanding that buildings should work with climate, that design matters more than energy consumption, that natural materials can perform remarkably well when used intelligently, that knowledge deserves to be remembered and applied. Because ultimately, the Viking climate control secret wasn't secret at all. It was simply paying attention to how the world actually works and designing accordingly. That approach remains as valid today as it was in the 9th century. Perhaps more so, as we face challenges of energy efficiency and sustainability that Vikings never imagined but solved instinctively through careful observation and thoughtful design.